All right, so this is 16.1, and this is going to be a relatively short one. This is integration. So we're going to introduce integration in the multivariable setting, and we're going to integrate over very, very simple regions. The really hard stuff is going to be coming up in the later sections, where we work with regions which are more than just rectangles, which is what we're working with here. Okay, so one variable calculus. We've got a function, we've got a graph. We're interested in the region from A to B, let's say. We can talk about the area under the graph, and so FAB, let's say of x dx. And the way you define this, and the way you often like to think about it, is you chop up your region into lots of tiny little pieces, and you draw these rectangles like this. For example, using the right endpoint as the height of the rectangle, right endpoint at the height of the graph. And you add up all the areas of the rectangles. And that's your first estimate for the area under the curve. You let the width of these rectangles go to 0. In other words, you use more and more of these, you break up AB into more and more tiny little segments. And as the number of segments goes to infinity, or as your rectangles get thinner and thinner and thinner, their size goes to 0, you actually end up with the area under the curve. All right, so let me kind of write it like this: equals sum of areas of rectangles. And let me put that in quotes, because that's definitely not the formal definition, right? But that's how we often like to think of it. All right, so in a multivariable setting, let's again kind of restrict ourselves to 2 variables, at least at the beginning. We are going to be looking at, if I draw the graph here, we're going to be looking at the area under the graph above a region, a rectangular region for this section. So we're going to be looking at something like that. And integral over the region, we're going to call the region R. Over the region R, f of x comma y, dA. That's going to be the area the volume under the graph of f of x comma y. All right. So instead of area, of course, it's going to be volume. We use dA as a general indicator that we're looking at the region of interest is 2-dimensional. So the A kind of stands for area, right? And regions in the plane have areas as opposed to lengths, or as opposed to volumes. All right. Okay. So how do we do this? Well, we're going to do this as usual in analogy to the one variable calculus setting. So in one variable calculus, the region that we're integrating over, the interval a to b, right, looks like this. And we're chopping up our interval into tiny little segments, right? Now we have a region which is rectangular, right? That's this region right down here, R. And we're going to chop it up into tiny little rectangles. So I'm going to do it like this, and then like this. Okay, so each of these rectangles, for example, this one here, is analogous to one of these segments in the one variable setting. Okay. All right. So in the one variable setting, for each of the segments, what we do is we take the height of the graph above, let's say, the right endpoint, and we draw a rectangle, and we calculate the area of that rectangle. That represents kind of a small chunk of the area underneath our entire curve. So now we're going to do exactly the same thing. We can't draw the picture kind of in a flat face like this, so I'm going to draw it in space. Here's our region. We're chopping it up into tiny little rectangles like this. And for each rectangle, we're going to take, for example, for this one right here, we're going to take the height above until we hit the graph. And this guy is going to have a volume because it's a box, a rectangular box. And so that little volume there, if you is a small bit of the volume underneath the graph. And if you add up all the volumes of each of these, above each of these little boxes, you're going to get essentially the volume under the graph, which is this double integral right there. All right, two integrals, at least for now, represents the fact that we're doing, we're working with two variables. All right. Okay, so that's the core idea, right? And again, as usual, if you want to get, so this you can think of as an estimate for the volume. And then as you let these rectangular boxes, as you let their sizes go to 0, your estimates get more and more and more accurate. And in the limit, right, you get the actual volume underneath the graph. Okay, so this guy here, again, I'm going to do a thing in quotes, is, so we said sum of area of rectangles. So this is going to be sum of area of volumes of rectangular boxes. And in huge quotes here, because this is definitely not, careful math. All right. So a couple notes. So we're talking about volume under the graph of f of x comma y. And just like in one variable calculus, when we talked about area under the graph of f of x, remember this area could be negative because if you have portions of the graph underneath the x-axis, then that counts as negative area. All right. So in the same exact way, when we say the word volume, we could have negative volume if you have parts of your the graph of your function. If parts of it live underneath the xy plane, right? That portion is going to count as negative volume. Okay. All right, so just be aware of that. It's exactly the same situation as in one variable calculus. Okay, so the real question is, how do we actually compute these things? Luckily for us, the idea is actually very simple. If I take a look at my box of interest right here, this is the region over which we're going to be integrating. And again, it's analogous to the AB in one variable calculus. Let's label this rectangular box. Let's call this A. Let's say this is B. Let's say this height is C. Let's say that height is D. Okay. All right. So we said we were chopping things up into tiny little rectangles. Okay. Let's do this. So we said the volume under the graph, the double integral, what we actually are looking for, is what you get when you add up the volumes of each of these tiny little thin boxes, rectangular boxes. Well, we have a choice in how to add these up, right? In one variable calculus, it was kind of clear. We just take, the first box, add it to the area of the second box, add it to the area of the third box, and so on. But now we have a kind of a grid of boxes. So we have a choice, do I want to add this box first to that one, and then that one to that one, or do I want to go downwards or whatever, right? So I have actually a lot of choices. So what I'm going to do is I'm going to add them up like this. I'm going to take the volume above this guy, and I'm going to add it to the volume above this guy. again, these volumes of just regular boxes, right? Add it to the volume of this, add it to the volume of this, add it to the volume of this. I'm going to add all those up, and I'm going to put the result right here. All right. Now, next, I'm going to do the exact same thing to the next column. So I'm going to take this one, take the volume of that the rectangular box that lives above this, rectangular box, rectangular box, rectangular box, rectangular box. I'm going to add them up. I'm going to put the answer there. All right. And I'm just going to keep doing this all the way down from A to B. All right. So I'm just going to represent it like this, right? Dot, dot, dot. Down here, and then dot, dot, dot. Like that. All right. So each of these blue dots represents the volume of kind of a strip of the rectangular box, a very thin strip. Okay. All right, but we want the volume of the entire volume, right, underneath the graph. So what we do next is we can add up in this direction, right, all the values that we got at the blue dot values, all right, which were the volumes of the strips. And of course, if you add up these values, your answer over here is going to be the volume underneath the graph, all right? So if you add all these guys up, you're going to get double integral f of x comma y dA over your region, okay? All right, now if I think of it this way, and I take smaller and smaller and smaller rectangular boxes, so I make this grid finer and finer and finer, one thing we can kind of observe is that A, B, C, D, I'm just drawing the same picture here. One thing we can observe is that when we add up these strips vertically, right, like this, add up this strip, essentially what's going on this blue strip right there is that the x value on that strip is constant, right? And on this strip right here, the x value is constant, okay? So when I actually do this adding of these rectangular boxes as they get more and more and more fine, right, what's happening is this guy here, the kind of answer that I get when I do the adding, these guys are actually just one variable integrals, one variable calculus integrals. And what are they? They actually represent, if I draw this in 3D, they represent, so this strip right there represents the area of the graph of my function that's above this small line segment right there. So it's going to represent that area right there. Okay? So each of these strips represents one of these areas. And essentially what I'm doing when I add them up at the end horizontally is I'm adding up the areas of these strips, kind of. And then, you know, if you, in a way, you can think of it as if I add up the areas of all the strips, then I'm going to get the volume, the total volume. All right. Okay, but why do I want to mention that? Well, the deal is these one variable calculus integrals are known, right? We know how to do one variable calculus integrals, right? And the important thing is that along, let's say this strip right here, down the strip, because x is constant, we're just doing a one variable integral where we're thinking of x as a constant, right? And for the second strip here, we're doing a one variable calculus integral where we're thinking of the x value as a different constant, right? Further along the x-axis. If we do the one here, we're doing a different, a one variable integral with a different x value, but the x value is constant, okay? So for each of these strips, what we're doing is we're integrating with respect to y, because y is the variable that's changing, right? We're going from y equals c to y equals d. Second one, we're going y equals c to y equals d, y equals c to y equals d. All right. So for example, if this middle value right there were, let's say, x equals 10, right? Then this strip right here, when we add up the area, like this picture right here, we're going to get integral. So this is, let's say again, at x equals 10. This is actually the one variable calculus integral f of 10 comma y dy And again, we're going from y equals c to y equals d. All right, so just one variable calculus. And this should be very reminiscent of what we did with partial derivatives. We were thinking of one of the variables as kind of moving and the other variable as constant. So in this example, we're thinking of, in a way, y as the moving variable, right? Y is, this f is a function of y and not x, because x is constant at 10. Okay? All right, so what we're doing is we're getting a lot of these one variable calculus integrals. This integral c to d, f at 10 comma y, dy, c to d, f of 10.0001 comma y, dy, c to d, f 10.0002 comma y, dy, right? So each of those three that I just mentioned correspond to one of these strips. All right. And again, at the end, what we're doing is we're adding up all the values down here horizontally. And what is that? Well, again, when you add things up, that's integration, right? So ultimately what you're doing is you're taking c to d, f, and then you're thinking of y as your variable. You're thinking of x as constant, right? But I'm going to put the x in here, right? But when you do this first integral here, these vertical strip integrals, you're thinking of x as a constant, okay? So when I do this integral, my answer is going to have an x in it, right? And if I wanted x equals 10, right, I would just plug in x equals 10. All right, but when I add up horizontally these values, what am I doing? That's an integral. That's an integral. And I'm going from what to what? I'm adding up all these values, right, starting from x equals a, and then I have strips going all the way from x equals a to x equals b, right? Every x value corresponds to a strip upstairs, right? X equals a corresponds to this first strip, x equals b corresponds to the last strip, and every one in between corresponds to a strip. And I want to add up all these strips, okay? So I'm essentially integrating from a to b of this guy in here, dx, okay? And so this is the volume under graph, okay? And of course, the more general notation, double integral over our region, f dA, all right? Okay, so normally we write this, we don't bother to write the parentheses, so I just write a to b, c to d, f of x comma y, dy, and then dx. Implicitly, meaning that I do this integral inside, it's going to give me a function of just x, because the y's integrate away when I input the limits of integration c to d. And then I just integrate a function that's just in the variable x. All right? Okay, so the first question is, before I even do any examples, I chose to do this with vertical strips, right? Well, what happens if you do this first with horizontal strips, right? Again, this is a to b, this is c to d. What happens if I add up these kind of rectangular boxes horizontally first, right? I add up the values of all these boxes, and I put the answer there. Add up the values of all these next boxes, put the answer there, and so on, right? And then I add them up at the end to get an answer there. Is that going to be the same thing? Well, it feels like it should be, because all we're doing is we're adding up these boxes in a different order, right? The first way we did it, the ordering was we add this one plus that 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 one. We added that up, got an answer. Then we added this one plus that 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 one and that one. And then we added and so on, right? But now we're doing it horizontally first, right? But in the end, you can kind of see we're adding up all the same boxes. So we should get the same answer, okay? So the deal is, if your function is nice enough, it is the same answer, all right? Basically, so this is, again, a situation very much like our discussion of differentiability. Most of the functions that we play with, well, for our class, the functions that we play with are all going to be fine. You can integrate horizontally first or vertically first. You'll get the same answer. In real life, there are functions that are absolutely horrible, and the order matters. All right, because what's happening is you're not literally adding up boxes because things are going to infinity. So the number of boxes are going to infinity, and there's always complications when you do that. And so there's a possibility where the kind of summing doesn't add up correctly. And that can definitely happen. But for our class, just like with differentiability, we're going to only deal with functions where everything is cool. All right. Okay, so from here on out, you can always assume you could do the ordering vertically first and then horizontally, or horizontally first and then vertically. Okay, so these two are equal. All right, if you're going to be a math major, you will, if you take an analysis class, very likely you'll talk about the fact that it's not necessarily equal in every single possible case. There's the fact that some functions are not nicely integrable. All right, I guess I should mention the fact that you can switch the orders, right? Do dy first or dx first. That's called Fubini's theorem. And again, we're not going to worry about it too much. Okay, well, we're not going to worry about it at all. Okay, so let me do an example. So luckily for us, we're only doing rectangular regions today in 16.1. So this is actually super, integration looks amazingly simple. Okay, so let's take a look at f of x comma y equals xy squared, just a random function. And let's say we're interested in the region where, I'm just going to draw a picture, where we're between 2, 4, and let's say 3, 10. All right. Not to scale, of course, but it doesn't really matter. Rectangular region, that's the important thing. Okay. All right. So x between 2 and 4, y between 3 and 10. All right. Okay, so let's calculate the volume. Volume under graph above this region is, again, our kind of notation for this is double integral f dA r, right? So we have this, so the deal is we have this kind of general notation because we can integrate in two different ways, right? So it's good to have one notation that's more abstract that represents just the fact that we're integrating over a region and doesn't necessarily kind of state that you're integrating in one particular order or the other. All right. Okay, so let's do our integral. Let's do the vertical integral first. And again, the way you do this is you just look at, if we're doing, okay, so here's my function, xy squared. I'm deciding right now, I want to do the dy first, the vertical integral first, and then dx. Okay? So the way you do this is we're doing the vertical integral first. So we're doing vertical strips. And so if I draw in my region picture a vertical strip, I can easily see the range of the integral, right? The range of the integral always starts at 3 and always ends at 10. All right? So this is going to be y equals 3 to y equals 10. And I'm always going to put the y equals just so that it keeps it so that I can catch mistakes more easily, right? So this one is with respect to y, right? And so x, this inner integral here, x is to be thought of as a constant, okay? And when I plug in y equals 3 to y equals 10, right, ultimately all the y's will disappear out of the problem. Okay, so what about the horizontal one? Well, strips, these strips start from x equals 2, and we want all the strips, right? We want all the strips until we get to x equals 4. That will cover the entire region. Okay, so 2 to 4. So x goes from 2 to x equals 4. All right. Now, of course, it might seem that I just wasted my time kind of explaining all that because it's pretty obvious, right? But in the next sections, we're going to be doing regions which are not rectangular, and it's really, really easy to mess up what your limits of your integrals have to be. So let's start out kind of being very disciplined with it, and so that in the future, when we get into far more complicated situations, we'll be more comfortable with it. Okay. So now let's just do it. So the way we do this is we just do the inner integral first. So the outside stuff just comes along for the ride, right? Dx. And then the inner integral, again, we just treat the x as constant. So we're essentially just integrating the y squared. The x comes along for a ride as a constant, so we just have a constant x in front. Integral of y squared is 1/3 y cubed. And we're evaluating that from y equals 3 to y equals 10. Okay. All right, now when we actually write that out, that's going to be x times 1/3 and then 10 cubed minus 3 cubed dx. And the reason I wanted to write this out is that at this point in your problem, there should be no more y's. All right, it's a really easy, silly mistake to make, especially in the later sections, where if you set the integrals up wrong, you'll see some y's at this point. If you do, you've done something wrong. Because at this point, you should only see x's. The y's should have disappeared once you plugged in your limits of integration. All right. Okay, so this is going to be, I'm just going to pull this constant out. 1/3, 10 cubed minus 3 cubed. And then it's just actually integral x, integral 2 to 4, x dx. And again, you see now, this is merely a one variable calculus integral, right? There's not even any other variable sitting here at all. And again, it represents kind of adding horizontally, right? And of course, at this point, when you're adding horizontally, there's no more y's. Each of these are just numbers that depend on the location that you're at in terms of x, okay? All right, so finally, this is going to be 1/3, oops. This is going to be 1/3, 10 cubed minus 3 cubed, and then the integral, we're going to get 1/2 x squared evaluated from x equals 2 to x equals 4. And so this is 1/3, 10 cubed minus 3 cubed. 1/2 4 squared minus 1/2 2 squared. Okay. And so let's just simplify that just for fun. This is 8 minus 2. So 6, so 2 times 1,000 minus 27. All right. So 2 times 973. All right. Now, the point here is that this is just a number, right? And that's better. That better be what you get as your answer. And it's a positive number, so there's more volume above the xy plane as opposed to below the xy plane. All right. Well, in fact, of course, with this function, if you think about it, everything was above the xy plane because it was just a function xy squared, right? But you always keep in mind that it could be legal that this is negative. Okay. If we had done it the other way, we would get the same answer. All right. So if I had done this, let me set it up the other way at least. So the other way would be, here's, we were going, sorry. Y is 3 to 10, x is 2 to 4. So this was 2, that's 4, that's 3, that's 10, right? If we set it up the other way, where we want to integrate horizontally first, then we represent that with horizontal lines, right, along our region. And we can see every horizontal line starts at x equals 2 and ends at x equals 4. So our limits of integration is x equals 2 to x equals 4. We're integrating dx first, right, to represent that the x's are changing. The y's are constant. Our function was xy squared. And then we're doing, after that, we're doing the integral with respect to y, where we're adding up all these horizontal segments. So the first segment starts at y equals 3. And then we could do a second segment, third segment, all the way up. until we get to y equals 10, and that fills up the entire region. All right, so y equals 3 to 10. And again, it seems silly that I'm doing it so carefully, but it'll really pay off when we do the complicated regions next time. Okay, and again, when we integrate, right, first you integrate the inside, and this time it's with respect to dx first, and then dy, right? So this is going to be y equals 3 to y equals 10. We integrate with respect to x, so we think of y as a constant, so the y squared just comes along for the ride. And so we have 1/2 x squared y squared evaluated from x equals 2 to x equals 4 dy. Once we plug that in, we have no more x's. So this is going to be 1/2 4 squared minus 2 squared, right? And then y squared dy, right? No more x's at this point. And it's just a one variable calculus integral with respect to y. And we might as well just finish it at this point. 4 squared minus 2 squared, 1/3 y cubed, y equals 3 to 10. And of course, this is exactly the same answer we got with our earlier order of integration. Okay. All right, and that's it. That's the idea behind integration for two variable functions. Very, very straightforward for rectangular regions. Okay, now let's extend this idea to functions of three variables or more, right? You can do exactly the same idea. A function of three variables. Again, in 16.1, we're just going to look at rectangular box region, right? So, of course, our region always lives in the domain of our function. In one variable calculus, the domain is just R. So the regions are line segments or portions of lines, right? Portion of the line. In two variable calculus, our domain is R2. It's the plane. So our region is a portion of the plane. So now in three variable calculus, our region is a portion of space. Okay, so a rectangular box in 16.1. So maybe something that looks like, oops, we're only doing rectangular boxes that are parallel to, whose edges are all parallel to the axes, to the coordinate axes. All right, so we would be integrating perhaps inside this this rectangular box. Okay. All right, of course, it's pretty much impossible to draw pictures at this point, so you always think back in analogy to the two variable situation. Okay, and of course, the formal mathematics is the same. We chop up this rectangular box into tiny little sub boxes. We calculate the integral, or the kind of four-dimensional volume for each of those little boxes, and we add them up. And this time, we have a choice of adding them up in three different orders, right? We can add up, for example, horizontally first, so in terms of the x-coordinates first, right? And if we do that, we add all of these up in terms of the x-coordinates, we're going to end up with a two-dimensional grid of answers. And then we add up those two-dimensional grids, maybe, let's say, in this way, right? So this is actually just two variable calculus at this point, right? We get some numbers here, and then we add those up that way. Okay, so what I've described here, if this is x, y, and z, I've integrated with respect to x first, equals something to x equals something. And then I've integrated, let's see, I've integrated vertically like this, so z equals something to z equals something, the appropriate numbers, right? And then I've done, finally, the y direction. Y equals something to y equals whatever is appropriate. Okay, and then my function here, and then I'm doing dx, dz, dy. All right, and again, we're only going to be playing with functions where it doesn't matter what order we do it in. So I could add these up in any order I like, and I'll get the same answer. Okay, so in this case, there's going to be a whole bunch of different orderings that we can do. All right. So the good news is, of course, in terms of mechanics, in terms of actually doing these integrals, it's exactly the same idea, right? This inner integral here, the first integral, the dx integral, you just integrate it, and you think of y and z as constants. And then once you've done that integral and you stuck in your limits of integration, your x's are gone. So when you do your next integral, the dz integral, right, you just have to think of y as a constant, right? And in this case, it's just a two-variable calculus problem at this point. And then when you do the dy integral, it's just a one-variable calculus problem. All right. Okay. So that's pretty much it. Very, very straightforward, at least our initial introduction to integration. It's going to get a lot more complicated, but for now, 16.1, we're very, very lucky. Okay, so the last concept I want to talk about here is, oh, and of course you can keep on doing, if you have four variable function, you just add one more integral and so on. Okay, so the last concept is the average value of a function, let's say f of x comma y. Just let's go back to two variables just for simplicity. And again, we are only interested in rectangular regions today, or at least for this lecture, right? So the average value of f is going to be literally the same idea as calculating the average value of a function in one variable calculus. How did you do that? Well, it was you integrate from a to b, f of x dx, right? So this is like calculating the average of your exam scores. You add up your exam, or your, let's say your homework scores. You add up all your homework scores, and you divide by how many homeworks you had. So here, the integral represents the adding up of the homework scores, and then the dividing by the length of the interval, a to b, so b minus a, that represents the dividing by how many homeworks you had. All right, so homework scores, how many homeworks you had. Okay, so that's my average, right? So now it's literally the same idea. Integral, let me just write the general form. So over the region R, let me call that R again, f dA, right? I have to divide, so this is the adding up, right, again, of my exam scores or whatever, and I have to divide by the number of exams. And in the previous case, in one variable calculus, I'm just dividing by the length of the interval that I'm integrating over. Now I have to divide by the area of the region I'm integrating over. So it's going to be b minus a times c minus d minus c. Okay, so this is just the area of R, and this b minus a was the length of a comma b. Okay, and of course you can imagine in the three variable calculus case, what's going to go in front is of course the volume of the region that you're integrating over. All right. Okay. I think that might be pretty much. Oh, notation. Sorry, I forgot three variable integral notation. F dv. And I think our book likes to use d for the regions, but that doesn't really matter. The important thing is the v, as opposed to the a. The v indicates volume. So that tells us we're working with a three variable problem, all right, essentially. And we can also see that with the triple integrals right here, okay? If you're doing more and more variables, the general notation, for example, as you get to 4, 5, 6, whatever, you would probably just stop with all these integrals. You just do this over your region, whatever you name it, R, D, doesn't matter. Let me call it D, and then F. And then you would probably still just use dv, all right? Just because it gets super unwieldy after that point. But again, we're generally just going to be integrating over integrating two variable functions and integrating three variable functions. So we're not going to worry about that too much. Okay, so just three variable functions is dv, two variable functions is dA, right? And one variable function is just what we had in one variable calculus. So f dx. And if we kind of write it in the same notation with this d here, this r here, we could write ab there to kind of make all these notations very much analogous. All right. Okay, so that's pretty much it. The problems in this section are very, very straightforward, which is great because you can spend more time on optimization.